tunnel diodes, the tunnel diode exhibit a special characteristics known as the negative resistance. This feature makes it useful in oscillators and microwave amplifier applications. Two alternate symbols are used, which can be seen in this figure. The tunnel diode symbol is this. Either you can use this symbol or this symbol. So the tunnel diodes are constructed with germanium or gallium arsenide by doping the P and N regions much more heavily than a conventional rectifier diodes. Mostly the tunnel diodes are made using the germanium or the gallium arsenide, GE and GAAS. Right? So these are the materials which people uses for the fabrication of or fabricating the tunnel diodes. So in this case, they dope the P and N regions, basically the P and N semiconductor regions, which forms the PN junction. They dope it heavily. That means the Fermi level in the N region will be close to the conduction band, and the Fermi level in the P type material will be close to the valence band, very close to the valence band. So we dope in such a way that this condition is satisfied, and also the number of free charge carriers will be the concentration or the density of free charge carrier or the concentration of free charge carriers. Basically, the concentration of electrons in the n side will be more. Similarly, the concentration of holes will be much higher than the what we just we use the p-n junction diodes. So that's what it heavily doped means. Basically, you dope it with a more number of p-type the impurities, and similarly, you dope it with the more number of n-type impurities in the n regions. We were seen in the very beginning classes what are the impurities, how to dope these to make more heavily doped systems on p-type and heavily doped n-type systems. So basically, the doping will do two jobs. One is it will improve or if you take the n-type material, if you dope it heavily, two things will happen. One, the Fermi level will move close to the conduction band. Second thing, the number of free charge carriers which are available for the conduction process will be more. So these are the two things which happen. That is basically because the Fermi level shifts close to the conduction band. Therefore, the even smaller energy, even the thermal energy sometimes is sufficient to bring the free charge carriers to the conduction band. We know that whenever the electrons are present in the conduction band, then only the transport properties can happen. So any for any kind of semiconductor device or any other operations, the electron should go to the conduction band to move freely. So in this case, if your Fermi level is close to the conduction band, the number of free charge carriers can easily move to the conduction band. As a result, you will end up with more number of free charge carriers. In other words, in other terms, if you dope it heavily, then the free electrons will be more, because we know that how the doping process happens. In that way, also you can imagine these the heavily doped systems. So this heavily doping results in extremely narrow depletion regions. So if you dope it heavily, the PN junction depletion region will be very narrow. Since we have a huge number of the electrons in the N type and P holes in the P type, uh, they will just the recombination process or the depletion region formation in the heavily doped system will be narrow, because we have huge more number of free charge carriers, the electrons and the N type and the holes in the P type region. Therefore, the ionic cores which are forming or the depletion region width will be very narrow. So the heavily doping allows conduction of for all the reverse voltage, so that there is no breakdown effect as the conventional rectifier diodes. So in the heavily doping systems, what happens? Conductions allows conduction for all reverse voltage, so that there is a no breakdown effect. So in the reverse biasing voltage, since the depletion region width is narrow, that means the energy which the electron has is sufficient enough to penetrate the potential barrier. You might have studied what is the tunneling process in quantum mechanics. There is a barrier. Either the electron can go to the barrier and cross to the other side, or it can penetrate in the through the barriers, right? The square wave potential, you might have studied how the electronic wave function varies in the when in the boundary condition and in the potential region and the other side. So basically it will tunnel through. So you might have seen the potential barrier when you're studying the potential barrier problems in the quantum mechanics. The similar phenomena is applicable, not similar, same phenomena is applies here. So the depletion region is narrow. When the depletion region is narrow, what will happen? The energy of the electron, whatever is having the energy of the electron in the room temperature, that is sufficient to tunnel through. That means instead of jumping the barrier and go to the other side, it will just pass into the through the tunnel, means it will pass through the barrier and go to the other side. This process is possible when the depletion region width is very narrow, because we are already doped with the heavily heavy impurities or the heavily doped systems. We know that the depletion region is narrow, so that results in the electrons to tunnel through these diodes at the barriers. So these are the two symbols, and as the extremely narrow depletion regions permits electron to tunnel through the PN junctions at very low forward bias voltage, and the diode acts as a conductors. So even with the small forward bias conditions, whatever the voltage we supply, that is enough to tunnel through the PN junctions. We know whenever we form a PN junction, there will be a depletion region. That depletion region will be very narrow in the heavily doped systems. However, the depletion region will be very very wider or very large length. The width of the depletion region will be very large in the case of lightly doped systems, semiconductors. And the diode acts as a conductor, because since it is passing to, I'll just show you the the energy level diagram, how the tunneling process happens in this tunnel diodes. So in the coming slides, so this is figure 2 shows between A and B the point B. So basically here you just see this. So this is the typical the current voltage characteristics of the tunnel diodes. So what happens? This is a figure in between A and figure. This is a figure shown in this figure. Okay, this is the shown figure. Here. A point at a point B, the forward bias begins to develop a barrier, and the current begins to decrease as the forward voltage continues to increase. That means at the point B, forward voltage begins to develop a barrier. So in this, what we do is we basically do the forward biasing. Basically, I think the tunnel diode will operate in the forward biasing conditions. Therefore, we just increase the voltage, forward bias voltage, from 0 to the required voltage. So the corresponding current we measure in the y-axis. So initially, we know that what is the forward biasing condition. The negative terminal of power supply will connect with the negative N-type semiconductor. Positive terminal will connect it to the p-type semiconductor. This is the forward bias condition. We know that. So therefore, what happens initially? The current increases, sort of a kind of ohmic behavior. Ohmic behavior. That means as you increase the current, voltage, the current increases in the V is equal to IRV. So at certain point of time, or at a certain point of voltage called the B point, right? So corresponding to this voltage, the so that in the diode, what happens? It begins to develop a barrier. That means at this point the barrier will start forming. That means I'll show you what is the barrier and how it happens. So, and as a result of that, since the barrier height, we know basically barrier means the potential required an electron. The barrier height means the potential required to an electron to cross that much require that much voltage to cross the potential barriers which is formed in the PN junction. When you are solving the PN junction problem, I have given what is the potential barrier is BBI basically. So that much voltage is required to cross an electron to go to the other side, means P side. So that is what happens at sufficiently high voltage. Basically, this voltage corresponding to this point, the barrier forms. Therefore, instead of this electron go through the tunneling process, it will just stop until the point of C. The current what we get is slowly decreasing. So after that, further if you increase the forward bias voltage, current further increases. This is due to the electron get sufficient energy to cross the barrier instead of tunneling. Instead of tunneling process, it cross the barrier and go. So therefore, during these electrons crossing the barrier, they get again the increase in energy. As you increase the potential energy, voltage basically, what happens? The number of free carriers which can move, or the number of carriers which can cross the barrier, is increasing as you increase the voltage, or the electrons get sufficient energy to cross the barrier, and therefore again your current increases in the forward biasing conditions. Basically, if you increase the forward bias conditions. So basically, what we do is this is basically the tunnel diode operates in this region. That means the negative resistance regions. So this is the tunnel diode operation region. That is a B to C region. What is called negative resistance regions? We can just see this. This is when you calculate the resistance in this region. So you take this point and this point. The slope is negative. Obviously, your corresponding The resistance what you measured is negative. Basically it is a physical significance. There is no mathematical the significance of this. So v is equal to IR, or del v is equal to del IR, so you can write it in that way. V is equal to IR. So R if you want to calculate, V by I. So del R if you want to calculate, so del V by del I. So basically this difference. So you just take the difference between these, it will give the del V, and if you take this difference, it will give del I. So correspondingly, what is the negative resistance which can vary in the negative resistance region? The difference in negative resistance can be calculated by using this del V by del I relation, right? So therefore, the tunnel diode operates in the negative resistance region, which basically happens in the forward bias conditions. So where the increase in the result, increase in the current, this effect is opposite to that described in the Ohm's law, where an increase in the voltage results in increase in the current. So basically this is a sort of forms the Ohm's law, but the only thing is this is a negative resistance. Only thing is this is negatively happening. That is basically it is decreasing, whereas it's supposed to increase, it is decreasing. However, it can, we can just follow the for calculating the resistance, the negative resistance difference, one can use the Ohm's law. Basically, this there is no mathematical significance, as I already told you. At point C, the diode begins to act as a conventional forward bias diode. So, because we know that in the conventional diode, the current what we get after the onset voltage, that is due to the forward bias conditions, and also the current is associated with the crossing the electrons through the potential barrier, not through the tunneling process. So therefore, after C voltage point, corresponding to the this voltage, let us say the VC voltage. Once the voltage crosses VC, the diode current what you get is through the barrier crossing of the electrons, not the tunneling process. So therefore, this behaves like a normal